Okay. All right, so we've seen separable equations, we've seen linear equations, now we move to the next type, which is really a more general form of separable exact equations. So now any first order ODE can certainly be written in this form, or maybe presented to you in this form. You have some function m of t and y plus some other function n of t is equal to 0. Another way it may see this in the homework is just multiplying both sides by dt. So we have m dt plus dy is equal to 0. Right? So we have both forms. Now, we go back to our usual way of representing the solution, some function big F of ty equaling 0, that maybe we can solve for an explicit solution y of t. And in the past, what I've done is taking this equation and differentiate it with respect to t. So we have df dt plus df dy dt is equal to 0. So I'm going to box this and this. The idea is we match up the two. Because if we look at what they have in common, the dy dt. So therefore, ft corresponds to m, fy corresponds to n. Now m and n, both are given to you. That defines the problem. So the question becomes this. Is there a function big F of ty such that df dt, or ft, is equal to m, and df dy is equal to n? Because if there is such a function, then the equation becomes much easier to solve. The reason being, if I know that my m and n satisfy both of these relationships, and I want capital F, so if these hold, how can I use one of these equations to figure out? So in other words, I know what df dt is, I know what df dy is. How do I get F from that? I could use either one of these equations, but what would I do? So df dt is known. You know the derivative. You want the original function. What do? You integrate. I can integrate this equation with respect to t. Or I can integrate this equation with respect to y. Now, if you do either one, there's going to be something left over, like your plus c, if you will. That's why we actually will need both. But the point is, if m and n satisfy this, that if such an f exists, we have a way of getting it. Now, but the answer to this question is not necessarily yes for just any old m and n. And here's why. Because what I can do now is, instead of integrating, if I differentiate both sides of this equation with respect to y. So fty must equal to my. And then I can take this equation and differentiate it with respect to t, and I get fyt is equal to dm dt. Now, these two must be equal. Therefore, the right sides must also be equal. So f exists only if this equation is satisfied. dm dy is equal to dn dt. So if you're given an equation like this, and you think if you already concluded it's not separable, so you can't use that approach. It's not linear either, so you can't use that approach either. So the next thing is you try treating it as what's called an exact equation. So if this condition holds, we call this equation exact. So you're given this problem and written this way or written this way, the differential form. So if you exclude the other approaches we've seen before, and you think maybe it's an exact equation. So the very first step, check that. Take a derivative in respect to y. Take a derivative and they match. If so, great. Then we can say the equation is exact, and we can try recovering f by integration. Now, so if these don't match, what that means is, so the equation is not exact, we can't just integrate one of these and get the correct f. It just won't work. What you can do instead is multiply the equation through by something that will hopefully make it exact. And that's called an integrating factor. Now, you've just seen integrating factors as linear equations. It's literally the same concept. So anything you can multiply the equation by to make it solvable just by straight integration, that's an integrating factor. It's just that if the equation is not linear, we have to get the integrating factor a different way. But they're called the same thing for a reason. Okay. But for now, I'm going to focus on the simpler case where you've given this equation, you've checked this condition, it holds up, the equation is exact. Now, what exactly do you do? All right. So if it is exact, the second step that you take is, you really can pick either one of these equations and integrate it. So I'll just pick the first one. So I can say that, so we know that f of ty is the integral of m with respect to t, also equal to n with respect to y. So I'm going to focus on this one. So I'm going to let m1 be the integral of m with respect to t. So actually, I would rather box this. Because remember, when I'm numbering steps here on the board, these are things that you actually do in working out the problem. So once you know it's exact, go ahead and do this. So the thing is, this is not exactly f, but it's part of f. Now, when you integrate this, don't bother with a plus c. Now, it seems kind of odd. It's like I'm telling you to do something wrong. The reason why it's going to be okay is there's going to be a second integral. The plus c will be included with that. So that's why it's okay to leave it out in this case. Now, so what do we know about f? We don't know the whole thing. But what we can say is that f that we're looking for is equal to this m1 that you just got, plus some function, unknown function of only y. So that's kind of playing the role of a plus c, if you will. Okay, but the reason why I'm telling you not to do it here is we want the constant integration over here, not part of this. Okay, now we need some way of solving for g that will complete f. So what you do is differentiate both sides of this with respect to y. So df dy is equal to the derivative with respect to y of m1 that you just got, plus g prime of y. Okay. This is not known, but this is. Now, what is this equal to? Well, df dy has to be equal to n that you're given. So you can fill that in over here. So now you know you have an equation for g prime. So g prime of y is equal to n minus the derivative of m1 with respect to y. So now you can solve for g by integrating again, this time with respect to y. So your third step is g of y is the integral of n minus dm1 dy with respect to y. And this time, you do want to include a plus c in case there's some initial condition that's given. So then, once you have all the pieces, then you can come back here. Your fourth and final step. Okay, let me box this one too. So everything you do is boxed. Okay, so integrate n with respect to t, then use that. Sorry, my parentheses misplaced. That should be an m1. I'd accidentally drawn a parenthesis over it. So integrate n with respect to t, use that to get an equation for g, integrate a second time with respect to y to get g, put the two pieces together, and then you have your big F. So then finally, your implicit solution is big F of ty equal to 0. And don't forget, you do want a plus c in there so that if there's initial condition, you can find out what c is. Okay, so check for exactness, integrate with respect to t, integrate with respect to y, put together your f, and then you can write down your solution. If an explicit solution is required, if that's in the problem statement, then you would take this equation and solve it for y. Questions up to this point? Okay, so now I will step through an example. Okay, so the given equation is y over t plus 6t plus natural log of t minus 2 dy dt is equal to 0. So identify your coefficients right off the bat. Whatever's multiplying dy dt, that is your n. Whatever is not, remember everything's on one side of the equation, set equal to 0. So the coefficient of dy dt is n, everything is not included in that is your m. All right. Now, check. Is this equation exact? So you take a derivative of m with respect to y. So in other words, t is treated as a constant. So what is the derivative of this with respect to y?
Same thing.
Not exactly the same thing. Because it's y, 1 over t treated like a constant.
Yeah.
So it's a linear function of y. Anyone?
Y squared.
You're going the wrong way, you're integrating.
So I'm differentiate.
Yeah, we're taking derivative with respect to y.
1 over t.
Yeah. So 1 over t is the constant. It's like when you're differentiating 2x, the derivative is 2. So this is 1 over t. And this is a constant, derivative of that is 0. Okay, so my is 1 over t. Then we take a derivative of n with respect to t. And what is that? Sorry, what?
1 over t minus 2.
1 over t, yes, but remember, 2 is a constant. Derivative of that with respect to anything would be 0. So you only get 1 over t. And they match. So the equation is exact. All right, so got to keep your differentiation rules straight. And remember, keep in mind which variable you differentiate in respect to. Make sure that it's differentiation when it's called for, integration when it's called for. Unfortunately, problems like this type of problem, you're literally doing both, but at different points. Right. Differentiate with respect to one variable. Any other variable is, think of it as a constant. Think of it as a specific number if you like, and work accordingly. So we're going to see more examples of these, that this kind of differentiation is not necessary. So any questions up to this point? Yes?
This is going to sound really dumb, but how did you get that y equals 1 over t?
Right. It's the differentiation rule involved here is called the constant multiple rule. Like example like 8, the derivative of 2x would just be 2. You're differentiating in respect to y. But 1 over t is a constant factor.
Okay.
So it stays. The derivative of y with respect to y would be 1.
Okay.
Okay.
All right. I see what you're doing now.
Okay. Anyone else? Other questions? Now that we know that it is exact, we can go through the rest of the process and get our implicit solution, capital F. So the first integral we carry out is m1 is the integral of m, so y over t plus 6t dt. All right. Now, and because we're integrating with respect to t, this time y is treated as a constant. So for example, I could write it this way. I could break this up into two integrals. It's not absolutely necessary, but it'd be easier to see what's going on. Now, in the first integral, because it's with respect to t, y is a constant. I can pull the y out and leave a 1 over t in here. And that's exactly the same idea as this. That's easier to see, more natural to you, that the 6, the constant factor of 6, can also be pulled out. So because we're integrating with respect to t, both of these are constants. Okay, so now, what would the integral be?
Natural log of t
Natural log of t with what?
with y.
Times y, yes. So y, natural log of t, and then for the other term,
3t squared.
yeah. So 6 times t squared over 2, but that simplifies to 3t squared. We don't bother with a plus c in this case because it's just going to come along later. So now we have our m1. Next, the other part of our solution is g of y. So that's going to be the integral of our n, so we'll throw that in first, minus the derivative of what we just got, so y natural log of t plus 3t squared with respect to let's see, t minus 2, okay. Yeah, the derivative of all that with respect to y, dy. So this is our m1. So we need to simplify all this, and in these kind of problems, it's always going to simplify a lot. In fact, what should happen, because we're about to integrate with respect to y, any dependence on t should end up going away through taking derivatives or canceling or whatever. If not, something went wrong. So I gave the equation wasn't exact after all. So, all right. So simplify the integrand. So we have natural log of t minus 2, that was there, minus derivative of this with respect to y.
Natural log of t.
Yeah, because ln t, constant factor, because we're differentiating with respect to y. And this won't give you anything, because there's no y dependence at all. So it's just going to be natural log of t. And sure enough, there's a lot of simplifying. The natural logs end up canceling. So in here, generally you're going to have a big mess, but you'll find that anything that depends on t is magically going to cancel. So what's left is just integral of minus 2 dy. So that's going to be minus 2y plus a constant. Okay. So that is our g. So now we can wrap up. So the function that implicitly describes our solution, big F of ty, is first piece, m1, plus the second piece, g. So it's y natural log of t plus 3t squared minus 2y plus c. Set equal to 0. Don't forget that. So whatever function you construct, the two pieces put together, set it equal to 0, and you're done. Yes?
What happened to the 3t squared in step 3?
From here to here?
From there to the solving for g.
Yeah, so what happens is, since I'm taking a derivative of this whole thing with respect to y, that's a constant.
Okay.
So it just goes away. Yeah, and a lot of that goes on in these kind of problems. All right. Now, unfortunately, this is a kind of equation that is not really, well, actually, no, wait, it is. it would be possible to solve for y explicitly if a problem requires it, because y is only involved in a linear way. We won't bother doing that here. If you were given an initial condition, you'd plug in your initial time here and here. You'd plug in your initial y value here and here, and then you can solve for c, and then you'd have a fully specified solution. Okay. So questions about this whole process? Okay. Okay. Now I'm going to do another one that does have an initial condition. So we have, so this is written in the other form for these kind of equations. 2x minus y dx plus 2y minus x dy is equal to 0. Initial condition, y1 is equal to 3. Okay. Now, so remember, y is your solution. Whatever's multiplying, in this case, dy, that is your n. And whatever's multiplying dx is your m. And you can always just divide through by dx if it's written in the other form. It's personal preference kind of thing. But yeah, sometimes a problem will be presented to you like this. Okay. So, again, check for exactness. So you want check it dm dy is equal to dn dx this time because it's now x instead of t. So what is the derivative of this with respect to y where x is treated as a constant?
Minus 1.
Yeah, it's minus 1. Okay, what about dn dx?
Respect to y.
With respect to x.
Minus 1.
Yeah, the subscript tells you what you're differentiating with respect to. Because it's contrived to be the exact equation, of course they're going to match. But soon we'll see ones where we don't match. Okay. Now, all right. I should mention before I continue, a separable equation is always exact. The distinction is that dm dy and dt, if you will, are both equal to 0. So that's the difference between a separable equation and one of these. Okay, so it is exact. Is there a question? Oh,
I figured it out. Thank you though.
okay. All right. So we get our m1 of xy. So that's going to be the integral of m with respect to x. So y here is treated as a constant. So what is that going to be?
X squared. X squared minus yx.
Yeah, because y is treated as a constant, so like the integral of say 4 is 4x. So in this case it would be yx, and we won't bother with a plus c here because it'll come along later. Okay. Next, the other part of our solution, g of y, is going to be the integral of n minus derivative of m1 with respect to x. No, with respect to y. dy. All right. So I'm going to go ahead and fill in all the pieces. So n is up here, so that's 2y minus x. Minus derivative with respect to y of this, x squared minus yx dy. So this is m1. Okay. Now, what's the derivative of this with respect to y? So x is treated as a constant.
Add minus x.
Minus x. The x squared contributes nothing because it's just by itself. There's no y involved. So that's going to be, all right, so 2y minus x was there before. Minus x dy. And sure enough, we have a minus x and then a minus of minus x. All that's going to cancel. So we just end up with 2y dy. So we just get y squared plus c. So that is the g part of the solution. All right. So then you put everything together. So big F xy is equal to m1, so x squared minus yx, plus this, so plus y squared plus a constant, is equal to 0. So that is our general solution. It implicitly describes y as a function of x. Questions up to this point before we deal with the initial condition? So for initial condition, we set x equal to 1, y equal to 3, and then that gives us a plus c. So we get 1 squared minus 3 times 1 plus 3 squared plus c is equal to 0. So what is c going to be as a result of all that?
-7.
Yes, because we have 1 minus 3 plus 9, so that adds up to 7. So 7 plus c is 0, so c turns out to be minus 7. So now we can put that back up here. So now we have an implicit solution anyway. So x squared minus yx plus y squared minus 7 is equal to 0. Actually, hold on. I'm going to put the terms in different order. You'll see why in a moment. All I'll do is I'll switch the x squared into y squared. I know it sounds silly, but you'll see why in a minute. And this is xy. So that's implicit. What if a problem required an explicit solution? We want to have a function y of x equals something. Now, we can't always solve for it, but in this case, we can. How do we solve that equation for y? Using an algebraic technique that you're all familiar with. Look at how y is involved in this. We have a y squared here. We have something times y there. What kind of equation? You think of it as an equation that doesn't y. And think of x as like it's a constant. What kind of equation is that you're familiar with? Yes, it's a quadratic equation. How do you solve that? You try factoring it, or if it doesn't factor nicely, what can you always do? Yeah, you can always do a quadratic formula. And I know that you all know that. So I found that students in general tend to be quite afraid of being wrong, of getting a wrong answer in the middle of class. I prefer someone who may be unsure if they have a right answer, but at least put something forth. I'm not going to denigrate someone because they put out a wrong answer, because at least they're making the attempt. Okay, so yes, we can use a quadratic formula where the coefficients, you think this is ax squared plus bx plus c equals 0, a general quadratic equation. A would be 1, b would be minus x, so there is multiplying the y, and c would be equal to the constant term, well, there's not multiplying any y, so that's x squared minus 7. So now, the quadratic formula would give us y of x is equal to x plus or minus square root of x squared minus 4 times a times c, so it would be x squared minus 7, all over 2a, which is 2. We can do a little simplifying underneath. So x plus or minus square root of minus 4 times minus 7 is 28 minus 3x squared all over 2. But the thing is, an initial value problem most times has a unique solution. So there can be only one. How do we determine which one, the plus or the minus? What's the way we can check? This actually came up before in an earlier section.
Plug in 1 for
What?
plug in 1 for x.
Yeah, use the initial condition. Yeah, and then it said plug in 1 for x. If you plug in 1 for x, you must get 3. So for instance, if I substitute in x equals 1, you get 1 square root of 25. So you get 1 plus or minus 5 all over 2. Well, only the plus sign is going to work. So I'm going to erase. So this is a solution because it satisfies the initial condition y of 1 is equal to 3. All right. So when a problem requires an explicit solution, if it happens to be a quadratic equation, it's either plus or minus. Use the initial condition to determine which sign is. Or that happens anytime your algebra ends up giving you more than one possible. Okay. So questions about this one? Okay. Now, in the examples I've shown you so far, the given equation turned out to be exact. But that's not going to happen. Fortunately, if it turns out not to be exact, it is possible to deal with it. Okay. That leads us to, or back to integrating factors. Okay. So let's suppose you are given an equation like this. You check, is my equal to nx, and you find that they don't match. So you can't proceed like before. So what you can do is, if m dx plus n dy equals 0 is not exact, you scale the equation. So you find a function that, like before, I would call mu, so that mu m dx plus mu n dy equals 0 is exact. Because you might be able to find a mu such that the derivative of mu times m with respect to y is equal to the derivative of mu times n with respect to x. Because if I can take a derivative of these expressions, I need to use a product rule. So if I go ahead and carry that out, so I have mu my plus mu ym on the left side. On the right side, I have mu nx plus mu xn. So now I need to find this mysterious function mu so that this equation holds instead of a previous one that turned out not to work out. Now, the problem is trying to find a mu of xy, function of two variables that satisfies this. Excuse me, it's generally going to be very difficult. Now, actually, well, before I proceed though, there are certain cases where it can be solved. So first I'm going to rearrange this. So any terms that involve just mu, not derivatives, I'll throw on one side and then everything else on the other side. So I'm going to have mu my minus nx, which we now know is non-zero because we want it to be 0 for an exact equation, but we know it's not. And that is equal to mu xn minus mu ym. Okay. Now, if we make an assumption about mu, we can actually solve this equation. So let's suppose that I assume that mu is a function of only x. So what that would mean is that mu y is equal to 0. So now I can ignore that last term, and I can rearrange. What I get is mu x over, actually, mu x, if I isolate that, is equal to my minus nx over n times mu. Okay. I actually know how to solve this equation. We've seen this kind of equation before. That if your solution, if a derivative is equal to the solution itself times some function, now, but the thing is, we're trying to solve for mu as a function of x. So if this part right here depends only on x. Okay. So that you form an expression my minus nx over n, simplify as much as you can. If it turns out to be a function of only x, then you'll recognize this from earlier sections, hopefully. Mu, the formula is e to the integral of my minus nx over n dx. So that is your integrating factor. In the case where that whole expression depends only on x. So what you can do is go ahead and try it. If your equation is not exact, form this expression. If it's a function of x only, great. There's your integrating factor. What if it's not? Then I do have a plan B for you. We just make the opposite assumption. Mu is a function of only y. So So mu x is equal to 0. So this term would be ignored. So now I give you this formula that's very similar. And now your integrating factor is a function of y. So it's e to the integral of nx minus my over m dy. And this must be a function of only y. All right, so your integrating factor, so you can try one or try the other. Notice the terms are flipped. Reason why it's opposite order is because there's a minus here. So you work out one integrating factor or the other, whichever one works, and then you go back to your original equation and actually multiply by it. Then the equation should be exact, and then you can do everything I showed you before. So you just have this interruption where you go off and find this integrating factor, put that into the equation, and now you can treat it as an exact equation because you just made it that way. Sorry to say that if neither one of these work out, like that's not a function of x, this is not a function of y, I don't have anything else for you. I can promise you that will not happen on a homework or test. So either the original equation will be exact, or you can do one of these two things to make it exact. So now what I'll do is show you how this procedure. All right, so the given equation is y dx plus 2xy minus e to the minus 2y dy is 0. Roll-Bauer conditional condition in this case. So this is your m. This is your n. So very first thing, check. Get dm dy, get dn dx. So derivative of m with respect to y.
One.
Yeah, it's just 1. And then take a derivative of this with respect to x. So any terms that involve only y, you can ignore them.
2y.
Yeah, 2y. It's only going to come from here. Okay. They do not match. So the equation is not exact. So I'm going to call this step 1a. Now we look at the expressions that go in integrating factors. So we look at, from the first option there, my minus nx all over n. And then we have nx minus my, so we just flip the terms here, divided by m. So we go ahead and fill in all the pieces, and we need either the first one to be a function of only x, or the second one to be a function of only y. Okay. So my is 1, and x is 2y, so that's what we have up top. And then numerator will just be the negation of that. And then we divide by n and then m respectively. So here, dividing by n, is 2xy minus e to the minus 2y. And here we divide by m, and that's just going to be y. So you check. Is the first one a function of only x, or is the second one a function of only y? It's pretty clear which one of these works out and which one doesn't. So that's the one that we'll use. Okay. Next, well, actually, so I'll call this step 1b, actually getting the integrating factor. So mu of y is e to the integral of this whole expression. So 2y minus 1 over y dy. Now that's kind of a mess. But so very important to simplify as much as you can along the way. So first we're going to simplify what we'll be integrating. So we break this up into two fractions. So 2y over y and then minus 1 over y. So e to the integral of 2 minus 1 over y. So now we can go ahead and integrate. And what will we get?
Y minus natural log of y.
2y minus natural log of y. Okay. Now, we want to simplify it as much as we can. The best way to do that, when we have a sum or difference of exponents, we break this up into a product. So now we have e to the 2y times e to the minus natural log of y. This law of exponents there. Now, e to the 2y is fine. We can leave it alone. E to the minus natural log of y, what can we do with that to simplify it a lot?
Cancel now.
We're going to cancel the e and the log. We have to do one thing first, though.
Bring down the negative sign.
Or not bring down, but bring up. Well, I guess it doesn't matter direction. But yeah, so I can move the minus there. So natural log of a to the b is equal to b natural log of a. So I had this and I changed it to that. So now you can cancel the e and the log. E to the 2y over y. So that is your integrating factor. Questions about getting the integrating factor before we use it? So now what you do is you go back to your original equation and you multiply through by the integrating factor. Okay. So mu m dx plus mu n dy is equal to 0. So in this case, filling in the m and n and the mu, we're going to have e to the 2y over y times y dx plus e to the 2y over y times the rest. So that's going to be 2xy minus e to the minus 2y dy is equal to 0. So now we have some simplifying to do. So in the first term, the y's cancel. So we have e to the 2y dx. And then if I take this and distribute it through, like in the first term, the y's are going to cancel. So I have 2x e to the 2y. And then in the second term, we have e to the 2y and e to the minus 2y. Those will cancel because you have basically e to the 2y over e to the 2y. So all you're going to have there is minus 1 over y. dy is equal to 0. So this is your new m, and this is your new n. Now, this equation should be exact because what you did to get the integrating factor. You don't have to check. I recommend it though, because that way you can make sure that you actually have the right integrating factor. So my, derivative of this with respect to y is what? What?
2e to the 2y.
Yeah, because the derivative exponential is itself times the derivative of the exponent, which is 2. So 2e to the 2y. And dn dx, you focus only on the x part. E to the 2y is a constant now. But the derivative of 2x is just going to be 2. So that would also be 2e to the 2y. So the integrating factor did its job, and it made the equation as a whole exact. What a miracle. So now you can go about getting a solution like in the previous examples. So we get m1, and that's the integral of m dx. So that's the integral of e to the 2y dx. But e to the 2y is a constant. So all you get is just x e to the 2y is your m1. So that's the first part of your solution. And then the other part, your g of y, so that's the integral of n minus dm1 dy dy. So we fill in what n is, so that's this whole mess. 2x e to the 2y minus 1 over y minus the derivative of this with respect to y. So now x is treated as a constant. All right, so we're going to have all this other stuff. So derivative of that would just be x times 2e to the 2y. That's an x. dy. And like always happens in these kind of problems, there's a ton of simplification. The 2x e to the 2y's will cancel. So all that's left is the integral of minus 1 over y dy, which is
Natural.
yeah, so don't forget the minus, natural log of y. Okay. All right, so that is the other part of your solution. So now you can put the two pieces together. So your implicit solution is so big F of xy, which equals x e to the 2y minus natural log of y plus c is equal to 0. So, and you're done. It's not possible to solve this, do any algebraic manipulations on this to solve for y explicitly as a function of x. If you did have additional condition, you could use that to solve for c, but that's all you can do. That's the final answer. Okay. So, questions about this one? All right. Now, there's one other kind of equation that requires a different approach. I'll use in the cover the last minutes that we have here. Okay. All right. This is actually a piece of section 2.5. So any ODE that can be written in this form, where your right dy dx is equal to some function of y over x, is said to be homogeneous, which is really unfortunate choice of term here because we're going to see another kind of equation later on is also called homogeneous. That's a very different meaning. But we will not do it for both equations, both types at the same time, I promise you that. Now, when it's possible to write your right-hand side as a function of only y over x, what you can do is make a change of variable. Let v equal to y over x. So now, the right-hand side simplifies. It's a function of f of v. So what he'd like to do now is solve for v instead of y, and then you can use this to go back to y. But the trouble is, you have dy dx over here. You have to express this in terms of v now. So what I'm going to do is I'm going to rearrange this. Vx is equal to y. And then what you can do is take a derivative of both sides with respect to x. So the left side is product rule, dv dx times x plus v times the derivative of x, which is 1. And that is equal to dy dx. So now you can go back to the original problem. I can take this expression for dy dx and put it in here. And now y is gone. I can express everything in terms of v now. So now I have v plus x dv dx is equal to whatever given function f of v. So this is the transformed equation. Okay. Now, why does this help? The reason why is this equation is separable. So the original equation, f of y over x, chances are, would not be. So what you can do is I can read to get so what I'll do first is multiply both sides. I'm going to put these two together, v minus f of v. Multiply both sides by dx. Okay, so now I have that. And then I do a whole lot of dividing. So now I have 1 over x dx plus 1 over v minus f of v dv is equal to 0. So now I can the form that we typically express separable equations in. So now I can give you a solution formula. So the integral of 1 over x dx plus the integral of 1 over v minus f of v dv is equal to 0. So now you can work out those two integrals and then you have v. So the idea is once you identify an equation as homogeneous, it's okay to just jump directly to this. So really, that's your first actual step. Work out those integrals, and then your final answer should be y of x equals something. But y is just equal to v times x. So you solve for v, multiply it by x, and then you're done. Okay. So I'm going to step through an example. Now, it may not be readily apparent at the beginning what f is. You may have to do some algebra up front to get it into that form. But I'll show you how you can do that in the example. Okay. So let's suppose the equation is given to you in this form. X squared plus 3xy plus y squared dx plus or minus x squared dy is equal to 0. Now, it seems like this looks like a kind of problem that you might try to solve using the approaches I've given you earlier, like is it an exact equation, integrating factor, and all that. So how do you know whether you should treat this as a homogeneous equation? Here's a tip. Look at the degree of all the terms. Every term, both m and n, is quadratic. If all terms, I can't write anymore. All terms have the same degree, then you can conclude as a homogeneous equation. So what you would do is you can write this, you can solve for dy dx by rearranging this. And what you get is x squared plus 3xy plus y squared all over x squared. But this is still not in the right form. We need it to be a function of y over x. So what you do is, since all terms have degree 2, divide top and bottom by x squared. That will enable you to express it in the form y over x. So what you'll get is, in the bottom you'll get 1. Up top you'll get 1 plus 3xy over x squared is 3y over x. And then y squared over x squared, so we can write it as y over x, the whole thing squared. So now we have 1 plus 3v plus v squared. That is your f of v. So anytime so if you're not sure what to do, like you see this equation in tests, not sure which approach to take, see if the terms have the same degree. Then you know that this is the approach you take. So now we can jump directly to the solution formula there. Integral of 1 over x dx plus integral of 1 over v minus this plus 3v plus v squared dv is equal. And then, the first integral is no problem, natural log of x. For this one, we have minus v squared plus 2v minus 1 dv. But what I'm going to route a minus. So I got to negate everything else. Okay. Wait, something's wrong here. Oh, that should also be a plus. Yes, okay. What can I do with that to simplify it? V squared plus 2V plus 1. Do you recognize that? Anybody? What? I can't hear you.
V plus 1 whole square.
Yeah, it's a perfect square. So this is V plus 1, the whole thing squared. So you can actually use, so I can write it this way, right, all this equals 0. L of x minus integral of V plus 1 to the minus 2 dV. And for that, you can actually use the power rule. The integral of that is equal to V plus 1 to the minus 1 over minus 1. And don't forget the plus c. So put another way, power rule is the integral of x shifted, like x minus c raised to the n. Power rule works exactly the same way. So I have ln x plus 1 over v plus 1 plus c is equal to 0. So now we have at least an implicit for v. Now, okay, I am officially out of time. The last two steps, you would rearrange that algebraically to solve for v. Minus 1 natural log of x plus c. And the very last step, multiply it by x to get y. So y of x is x, or minus x over ln x plus c. And that is the final result. So if the equation is homogeneous, the function of y over x, that is your f. And then you can jump directly to this solution formula, because I remember this. Just remember that the equation is separable, treated as a separable equation. Okay.